Okay, good afternoon, and welcome back to the weekly live discussions on the course ME92, Mechanics and Control of Robotic Manipulators. I'm Isaac John. I'm from IIT Palakkad, and I'll be the TA who will be dealing with this weekly live tutorial sessions. So, yeah, for this week, the syllabus for our discussions would be from points 1 to 4, right? Because if we have followed lectures, we have covered a brief introduction to differential kinematics. We have also derived the equations for velocity propagation models for serial robots. Velocity propagation model basically covers with how the linear as well as angular velocity propagates from base to the end effector for any kind of robotic manipulators. And also, Professor Shantakumar has also demonstrated how to perform a velocity propagation for any such manipulator using MATLAB. We have also used the theories behind velocity propagations to understand manipulator statics as well as workspace singularities. Because if you have gone through the lectures, you might have noticed a reciprocal relationship between the differential kinematics and statics of a serial robotic manipulator. And towards the tail end of the week, we have also covered a brief introduction to robodynamics, where we would derive the dynamic equations of motion using two methods, namely the Lagrange-Euler method and the Newton-Euler method. So for the purposes of this tutorial, because the main idea of this tutorial is to assist you or to give you practice to solve questions for quiz 4. And for the quiz 4, we'll be covering the syllabus for quiz 4 would be topics from points 1 to 4. And the dynamics, that is from points 5 to 6, would be saved for next week, right? So we'll look in more detail about the dynamics during the next week's tutorial session. Okay, so moving on. So until now, we have covered the geometrical model of robot kinematics or robot manipulators, which can be expressed as per this function, right? Where the vector mu would usually describe the task space variables of a robot. Task space variables. And the vector q would typically mean the joint space variables. Right? I hope we are now clear about what are task space variables and joint space variables. Like, for example, I'll give an overview for a 2R robot comprising of two revolute joints, because that's why we call it as 2R robot. So I'll label this axis as Z1, and I'll label the second revolute joint as Z2. Yeah, the configuration of this robot would be fully defined by two joint variables that are theta1 and theta2. So in this case, the joint variables would be theta1 and theta2, and the task space variables would be the Cartesian coordinates of this end effector, which is defined by the quantities x and y. Right. So in any typical robot, the joint space variables would be the variables like theta1 and theta2, rotation angles of revolute joints, or the slider distance of prismatic joints. And these variables basically fully define the configuration of a robot manipulator. And the task space variables are the Cartesian coordinates, position coordinates, as well as orientation coordinates for the end effector point. Right. So until now, we have covered the geometrical modeling, which maps the joint variables to the task variables in one direction or the opposite direction. So we call either of these problems as forward kinematics and inverse kinematics. So now we deal with forward differential kinematics and inverse differential kinematics, which would correspond to like in the forward sense for a very differential uh, increment in or for a differential change in the joint variables, what would be the differential change in the task variables, and the inverse problem as well. Like for example, in case of a differential change in the task space variables, what would be the differential change in joint variables? So this is also true in case of velocities. Like for example, if you are given the velocities of the task space, maybe theta 1 dot and theta 2 dot, what would be the velocity in task space variables, right? And also the inverse, the opposite way. Like if you are given the task space variables, what would be the joint space variables? So similar to how the geometric model are mapped using this equation, the velocity models can be mapped using this equation, either the forward or the inverse problem, which is defined there exists a linear mapping from the joint space velocities to the task space velocities, and the linear mapping is actually carried on by this matrix, which we would call this as Jacobian matrix. And this is nothing but the partial derivative of the task space variables with respect to the partial derivative of joint space variables. Right? For example, if you are given a function of mu as a function of q, then mu dot would be dou f1 by dou q1, dou f2 by dou q2, all the way to, sorry, dou f1 by dou q2, so and so. And it's also the same in case of column wise, dou fn by dou q1, all the way to dou fn by dou q. Yeah. Because depending on the robot manipulator, the function could be a vector function, and the task space variables could be q1 dot, q2 dot, all the way to q n dot. There could be m equations and there could be m mappings from m functions from joint space to task space and n joint variables in task space. So that is how you derive the Jacobian matrix. We'll cover that in more detail in the subsequent slides. And the case of forward differential kinematic modeling is more or less similar to simulating or analyzing the manipulator at velocity level. For example, if you give some inputs as q dot, for example, if you want to give some velocities into the motors at the two revolute joints, R1 and R2, suppose, like, for example, if I give 5 radians per second for the first revolute joint and 6 radians per second at the second revolute joint, what would be the velocities at the end effector? Maybe x dot and y dot. Right? Look, it's more like simulating the robot at velocity level. So that's why we call the forward differential kinematics as simulating or analyzing the manipulator at velocity level. And the inverse problem, like for example, if you are given x dot and y dot, right? If you are given, if you require your end effector to achieve some velocities, x dot and y dot, what should be the inputs that you should be giving to the motors, theta 1 dot and theta 2? So that is the problem of inverse differential kinematic modeling, which is more or less controlling the robot manipulator at velocity levels, right? So like you would use the inverse differential kinematics model once you get into robot control, robot motion control in the subsequent weeks, where you would use this relation to, to control a robotic manipulator, right? Okay, so typically, in case of robotic manipulators, such as what we have analyzed over here, the number of task space variables is 2, or maybe m, theta 1 and theta 2. And the number of joint variables would be, again, more or less same as the number of task space variables, x and y. So the number of task space and joint space variables in typical robotic manipulators are equal. So that makes the Jacobian square matrix, right? So if you want to do a forward mapping, we simply have to derive a Jacobian matrix like so, and multiply that with the given input to the join variables. And if you want to find the inverse problem, you will have to take the inverse of this matrix and multiply it with your desired end effector velocities. And taking an inverse when the Jacobian matrix is square is fairly straightforward. But there could be instances where the Jacobian matrix is not square. Maybe there could be more number of inputs than the controllable degrees of freedom, or the inverse case. There could be less number of inputs, but the number of degrees of freedom that you wish to control would be more than that. So in either of these cases, the Jacobian matrix cannot be a square matrix. So then how would you solve this inverse problem? So that is where we would use something called a pseudo inverse, and we will look at these cases one by one. So the first case, So the first case is when there are more number of equations than there are the unknowns. For example, if there is, I'll write it down. Like when there are more number of equations to be controlled. So like, for example, if you have a robotic manipulator, like for example, this 2R robot, right? I'll call this as R1 and this is R2. And the number of inputs that you can have is theta1 for the first revolute joint and theta2 for the second revolute joint. And for example, consider you want to control 3 degrees of freedom for this end effector. Maybe, for example, x, y, and theta. Right? You may want to control 2 positions and 1 orientation using a 2R manipulator. So now what will happen? So the forward mapping would be something like this. Mu dot would be J of Q. I'll write this with a different time so that it can stand out. Mu dot would be J of Q times Q dot. So mu dot would be the number of task space variables. So in this case, that would be 3. So mu dot would be 3 cross 1. And Q dot is the number of inputs that you are giving onto the robot. That is 2 cross 1. So that will be 2 cross 1. And that makes the Jacobian matrix 3 cross 2. Right? So in the case, for example, if you want to control the 3 degrees of freedom in the task space with only 2 degrees of freedom, the Jacobian matrix in that case would be a non-square matrix. So in this specific example, when there are more number of equations than the unknowns, the Jacobian matrix would look like a tall matrix, right? So it's not really possible to solve 3 equations with 2 unknowns because the system is overspecified, right? So like if all the 3 equations are independent, you cannot solve 3 equations for 2 unknowns because they are overspecified. And because of that, an exact solution may not exist. Right? Due to the fact that there are more equations than unknowns, the solution may not exist. But we can solve this sort of problem by using this principle. We can actually find an approximate solution. It's not an exact solution, but we can find an approximate solution using the principles of least square, right? So like, for example, we know that the mapping is mu dot is J of Q times Q dot. And this can never be equal, right? This cannot be equal when the system is overspecified. But if you want to solve for Q dot, right? The most common way, or the most accepted solution, is to find out an approximate solution such that the least square between this desired mu dot and this term j of q times mu q dot is minimized. So your objective is to find out q dots such that the least square distance between mu dot and j of q times q dot is minimum. So you can formulate the problem like this. This is how you formulate the problem. So the norm of mu dot minus j of q multiplied by q dot, we call this as our objective function, right? And you can also write this equation like this, right? A norm of a vector, or the least squares of a vector, is nothing but that vector itself transposed multiplied by that vector, right? Like for example, if this entire vector, if mu minus j of q multiplied by q dot is 3 cross 1, I'll write this over here. Mu dot minus j of q times q dot. So this and the size of this entire vector is 3 cross 1, right? So that makes the size of the transpose to be 1 cross 3, and this to be 3 cross 1, right? So the product of these two vectors would be 1 cross 1, right? And that makes it as a scalar objective function that we want to minimize. This is what we want to minimize, this scalar objective function with respect to q dot. So if you take the partial derivative of this objective function with respect to q dot, and remember that this q dot is a vector, that is a vector of joint coordinates. So if you take the derivative of the objective function with respect to q dot and equate it to 0, so this is what we get. So this is nothing but a square of some term. So the remainder would be the derivative would be something like this, right? Mu dot minus j of q multiplied by q dot, the whole transpose multiplied by j of q times q dot. I hope that is clear. If you take the derivative of q dot, because essentially this term is a square of itself. So something like x square. So derivative of x square with respect to x would be nothing but 2x, right? So that's why I have simply removed that 2 because the right hand side is 0. So 2 is neglected, and there's a coefficient in front of q dot, so that is carried over here, right? So now what will be the order of this? This would still be 1 cross 3, and the Jacobian matrix would be 3. 3 cross 2. Sorry, 3 cross 2 or something. So this makes it 1 cross 2. So if I'm expanding this derivative, what if I'm expanding this derivative? So this is the first term, multiplying mu dot by j of q, that is this term over here. And if I'm multiplying this term with respect to this term, that is this term, right? That will be, what I've done is I've multiplied the second terms out, j of q, q dot, transpose. Yeah, like if I take the transpose, what will it look like? I'll expand this equation over here, downward. So this will be mu dot transpose minus q dot transpose j of q transpose j of q. Right? Because this is a product of two terms. So AB, the whole transpose, would nothing but B transpose A transpose. So that is why I've inverted the ordering of these things while I take the transpose. So now we get Q transpose, J of Q transpose. And if I take everything, if I write it like this, I can simply rearrange it in this form, right? mu dot transpose multiplying by j of q, that is on one side. And on the other side, we have this term over here, q dot transpose j of q transpose j of q, right? And again, if I'm taking transpose on both of these sides, right? So that becomes this term j of q transpose mu dot, that is what we have over here. And if I take the transpose of this side, that will become j of q transpose j of q q dot, right? Nothing, if I apply this A, B, the whole transpose, we get B transpose, A transpose. That is what I have applied here. Now,
Sir,
what will be
sir, one
yes,
more time, sir.
yeah.
How we are taking the transpose, sir? This
We
step, fourth one. Oh.
Fourth one. Are you asking how we are getting
Sir.
from
The
to three
same
to
thing,
four?
same thing. What we are discussing. Transpose to the equation 3.
Okay, so if I take the equation 3, if I am taking the transpose of RHS, sorry, LHS, what will we get? That will be J of Q transpose mu dot, right? Because there is already a mu dot transpose, so mu dot transpose, the whole transpose would be mu dot.
Sir, that means AB, like two matrices, AB transpose will be B transpose into A transpose, sir?
Yes.
Okay, sir.
So if you consider this as A and this as B, so the transpose would be B transpose A transpose. So B
Okay, sir.
transpose would be J of Q transpose, and A transpose is mu dot transpose the whole transpose. That will be mu dot itself.
Okay, sir.
Right? So that is the left hand side. And similarly, transpose of RHS. So if I write transpose of RHS, so transpose of these three terms. So that makes it, first you have to take the transpose of this term. So the first term would be transpose of this term. That will be J of Q transpose. So this is the first term. Now the second term would be you have to take the transpose of this term. So that is J of Q transpose, the whole transpose. That is J of Q itself. And the third term would be this term, Q dot transpose, the whole transpose. That is Q dot. Right? So this term comes over here, and this term comes over here. I hope that is clear.
Yes, sir.
Yeah. So yeah, once you have obtained this equation, your objective is to find this Q dot, right? The controllable inputs that you have to give to the revolute joints so that you can reach very close to this final desired configuration. It's not an exact solution, but it's only an approximate solution, which minimizes the least square error between these two terms. So how do
Sir,
you get
how we are getting equation 5, sir?
equation 5? You have to take this matrix, take its inverse, and pre-multiply that with pre-multiply to this side.
Okay, sir.
Right? So if I take this part, what will be the inverse of this part? So that will be J of Q transpose J of Q, the whole inverse. Then if I pre-multiply this term with this left-hand side, what will we get? That will be J of Q transpose mu dot. This will be Q dot.
Okay, sir.
That is how you get equation 5. Right? J of Q transpose J of Q, the whole inverse multiplied by J of Q transpose mu dot. So this is what we call the least square error solution Q dot. Because if the matrix was square, you could have simply taken Q dot would be J of Q inverse mu dot. But if the matrix is square and if there are more number of equations than the unknowns, you have to use this thing. It's called the pseudo inverse. This entire thing is called the pseudo inverse. Instead of a regular inverse, this entire term, we call this as pseudo inverse. And in this case, we call this entire term as the left pseudo inverse. Right? And we use this left pseudo inverse when there are more number of equations than unknowns. Right? So if there are more number of equations or if our Jacobian matrix is tall, we use this left pseudo inverse to solve for Q dot. So that is one case. And we have actually one more case, that is when there are more unknowns than there are equations. When there are more unknowns. So in that case, the system is underspecified. Like for example, I'll give you another example. Like instead of a 2-hour robot, we have a 3-hour robot. 1, 2, 3. So I'll label this as the input to the first revolute joint as theta1, input to the second revolute joint as theta2. I'll label this as R2, and input to the third revolute joint as theta3. This would be R3. And suppose you only need to control two variables, x and y, right? You only need to control two variables on the Cartesian space, but you have three variables. So how would the forward differential kinematics looks like? Mu dot would be J of Q times Q dot, and mu dot is a 2x1 matrix, Q dot is a 3x1 matrix, and the Jacobian would be a 2x3 matrix. So like when there are more number of unknowns than equations, right? So in this case, your objective is for a desired x and y, what would be the inputs theta1 dot, theta2 dot, and theta3 dot. So these would be the unknowns actually, right? Q dot would be the unknowns. And if there are more number of unknowns than the number of equations, how would you solve for these unknowns? So in this case, the Jacobian matrix, in this specific example, it's a 2x3 matrix, or in this example, it will be a very wide matrix. Earlier case, it was a tall matrix. Now it's a wide matrix, m cross n. Here, m would be less than n. So now the system is basically underspecified, right? And if the equations are again linearly independent, we can have more number of solutions, right? For example, if you fix theta1, you can or if you consider theta1 as a free variable, you can solve this equation in terms of theta1, right? X and y will be in terms of theta1, or you can define theta3 as a free variable. You can solve this equation in terms of theta3, but there will always be infinite number of solutions because there are more unknowns than the equations. And now we have a question. If there are infinite solutions, which solution should we select? So that is the question that we wanted to answer. If there are multiple solutions or if there are infinite solutions, which solution should we select for satisfying this inverse problem? So typically, out of all these infinite solutions, what we would select is the solution that has minimum norm. Right? I'll give you one example what minimum norm is. So like, for example, if Q solution 1 would be something like this, QS1 dot, Q solution 1, first join variable, Q solution 2, first join variable, Q solution 1, second join variable, Q solution 1, the third join variable, etc., etc. And Q solution 2 would be another vector which has the elements Q solution 2, the first variable, Q solution 2, second variable, and Q solution 3, Q solution 2, the third variable. And so, like we have multiple solutions, Q solution N, things like that. So out of all the solutions, we would mostly go with the solution that has the minimum norm, right? So norm of a vector is nothing but, if you have a vector Q or Q dot, the norm would be Q dot transpose Q square root of. That is the norm of that vector. For example, if you have a vector, if you have a vector like this, A, B, C, the norm of that vector is A square plus B square plus C square under root. So out of all the solution, you will select the solution that has the minimal norm. And the reason that we would do is minimum norm or square of this norm is more or less proportional to the energy that you would require to move a robot. Right? Like, for example, if you are talking about kinetic energy is proportional to the velocity squared. So if you're taking the square of the norm, the solution that has minimum norm square, right? If a solution that has minimum norm or minimum norm square, you can easily correlate that solution with the solution that requires minimal energy associated with minimal energy. So you would mostly go with the solution that consumes minimum energy to go to this decide task-based variables, right? So now instead of the least square objective function that you have used earlier, now your objective function would be to minimize the vector of q dot subjected to these constraints. Okay. So this is our constraint. We have to strictly follow this constraint. Otherwise, mu dot and q dot may not be, that mapping will be lost. And in this case, our objective would be to minimize q dot such that these constraints are satisfied. And the way that we would formulate that problem would be like this. This is our objective function. And this term is that norm. This term corresponds to the norm of that q vector. And this term corresponds to the constraint. Constraints. So this becomes a typical constraint optimization problem where you have to minimize something subjected to some constraints. And over here is something, we have a parameter here called Lagrange multipliers. Lagrange multipliers. And this is similar to the weights that you would attach to each of these constraints, right? So depending on which constraint is more important, you can give more weight to that specific constraint using this Lagrange multiplier. So yeah, now you have two unknowns. Your objective is to find out the q dot, which has the minimum norm. So you have to minimize this objective function with respect to two variables. The first is this one, q dot, and the second is this lambda, because that is also an unknown that we have assigned. So to do that, we have to first take the partial derivatives of the objective function with respect to q dot and with respect to lambda, and equate it to 0 to solve for q dot and lambda. So the first equation, if you take the derivative of the objective function with respect to q dot, you will get this expression. So this is nothing but q dot square. So derivative of q dot square with respect to q is 2q dot transpose q. Sorry, 2q dot transpose. So that is what we have carried it over here, right? And if you take the partial derivative of this term with respect to q dot, the terms remaining would be lambda times multiplied by j of q, right? That will be the coefficients of q dot from this expression, that is j of q and lambda transpose. And similarly, if you take the partial derivative of this expression with respect to lambda, that is here, so the only term that remains is this term, right? The coefficient of lambda. Since this term does not have any lambda terms, derivative of this term with respect to lambda becomes 0. And derivative of this term with respect to lambda is simply this. That is nothing but the coefficient of lambda. Now you have two equations, right? And from this equation, equation 7a, you have to determine q dot in terms of lambda. So like I'll write this example from 7a. So if I take the transpose of 7a, I'll write it over here. Taking the transpose, what will we get? We'll get q dot. I'm taking this term to the other side of the equation. And if I take the transpose of this term, what will you get? If you consider this,
JQ transpose into
yeah, that'll be
lambda.
J transpose lambda. And there's also a by 2, right? Because there is a 2 here, right? So yeah, that is what we have over here in equation 8, right? And if I substitute this thing, equation 8, into this equation, right? Instead of q dot, I substitute this term into equation 7b, I'll get this equation, right? If I can write it down. So equation 7b implies mu dot is
Okay, sir. I got it.
okay.
Okay, sir.
Okay, sir. Fine. Okay, so now you got this equation, this expression, and finally, once you can back substitute this equation for lambda, actually. So what you would do this, let me see if I get this correct. Yeah. So JF2 times lambda. I think I may have I may have done this in the wrong order of this equation. So let me try this in a different way, just to make it more clear. I think it's better if I probably add a page, if that is possible. Okay,
So
I'll
simply writing converting 7b into directly it will come now, sir. Directly
7b.
converting 7. Lambda here it is there. Right
But
side lambda is there.
we don't have, we have to eliminate everything from equation. We have to eliminate everything from lambda. So I'll probably just quickly write it over here, maybe if that is the case. So dou L by dou Q dot would be, if I go back, it'll be Q dot minus lambda transpose J of Q, that'll be 0. I'll label this as equation, here in this case, it was equation 7a. And from here, how do I solve for q dot? Q dot would be J of Q transpose lambda by 2. I label this as equation 8, right? And dou L by dou lambda equal to 0. That was nothing but mu dot minus J of Q dot. This will be equal to 0. And I label this as equation 9. And if I substitute equation 8 in equation 9, what will I get? This will be, this will now becomes mu dot would be J of Q multiplied by, J of Q transpose lambda by 2. So now if from this equation, if I solve lambda, what will I get? So lambda would be 2 mu dot. Then I have to pre-multiply this with J of Q transpose the whole inverse. Hope that is clear. From this equation, I am solving lambda.
Yes,
so
sir.
I'll get equation 10.
Okay, sir.
And if I substitute this equation 10, this lambda back to this equation, all the way to equation 8. I'm sorry if I'm making a bit of a mess. So if substituting equation 10 in equation 8, it will be Q dot would be J of Q transpose by 2, right? This term over here, and instead of lambda, I'll write this term like this. Instead of lambda, we have J of Q transpose the whole inverse multiplied by 2 mu dot. So this 2 and this 2 will get cancelled. So that makes our Q dot as J of Q transpose J of Q transpose the whole inverse mu dot. Right? So for an underdetermined system, we use this matrix. We call this specific term as the pseudo right inverse. So this term over here, right? The matrix, matrix that is a coefficient to this mu dot, we will call this as the pseudo right inverse. So earlier, like when there were more number of equations than are known, we used the pseudo left inverse, which would give you the least square solution of Q. And when there are more number of unknowns than there are equations, we would use the pseudo left inverse so that we will get a minimum nor solution of Q dot for a desired mu dot. Right? So yeah, that is how that derivation would basically come. It's nothing but a manipulation of these two equations. So depending on the scenario, you will have to either use the pseudo left inverse or the pseudo right inverse. And the next stage that we considered was the velocity propagation models. For example, if you want to propagate velocities in case of a 2R robot like this, I'll call this R1 and R2. And I'll label this axes as Z1 and Z2. And the final velocities of the end effector would be x dot and y dot. So what this velocity propagation model is, it will propagate the velocities from starting from base all the way to the final end effector, right? And there is always an initial condition, because in case of fixed robot manipulator, the velocity of the base would be always 0 because the base is fixed. And the velocity propagation would be further contributed by the individual velocities of each of these individual velocities contributed by the individual joints. For example, if the first joint has a velocity of theta1 dot, that is what we are giving, and the second velocity has a velocity of theta2 dot. So these two inputs would contribute to the velocities of any point of any of these links. So as you propagate from all the base from base to the end effector, the contribution of these individual velocities would add up, and the cumulative effect would be reflected at the tip of this end effector. So to map that, we use this velocity propagation model. And the basic principle is derived as follows. So this is nothing but a simple demonstration of taking a derivative of a vector in frame of with respect to rotational frame of reference. So I'll demonstrate that. So like if you have a fixed frame of reference like this, I label this as frame A, and let this be XA, let this be YA, and let this be ZA. And we have another frame of reference that is rotating with respect to frame A. I label this as frame B, and the coordinates axis would be XB, YB, and ZB. And suppose we have a point Q that is attached on frame B, right? And the relative position of frame B with respect to A is specified by this vector, position vector of B with respect to A, that is a vector. And if you want to find out the position vector of Q with respect to A, the position vector of Q with respect to A, how would you write this equation? So the position vector of Q with respect to A is position vector of frame B with respect to A plus position vector of Q with respect to B. Position vector of Q with respect to B. So if you simply write this vector equation, this is what you get. Position vector of Q with respect to A is position vector of B with respect to A plus position vector of Q with respect to B, right? But notice that all the frames are should be written in terms of a single frame of reference. So the first two terms are written with respect to frame A, but the third term, this vector is actually defined with respect to frame B. So to convert this reference frame B to reference frame A, we pre-multiply that with the rotation matrix of B with respect to A. So that is what this equation is. Now all the terms are written in terms of the coordinate frame A. That is only the position. And now if you want to find out the velocities, you have to take the derivative of this equation, right? You have to take the derivative of that equation with respect to time. So what will happen? So taking the derivative, right? Derivative of P with the position vector of Q with respect to A, this would be, if I'm taking derivative of this position vector, then for the second term, you will have to apply the chain rule, right? First term multiplied by the derivative of second, right? Plus the derivative of the first term multiplied by the second term. This equation. Right? But there is, what would be the derivative of this rotation matrix? So if you are given a rotation matrix, the derivative of this rotation matrix is nothing but the angular velocity omega cross that rotation matrix of E with respect to A. So derivative of rotation matrix is the angular velocity vector multiplied by that rotation metric itself. Right? You can also, instead of this cross product, you can also write it in this way, omega tilde transpose rotation matrix ARB. Because you can always replace a cross product with a matrix multiplication. If you find this convenient, instead of a cross product, you can always use this. And for example, if omega is omega x, omega y, omega z, this the cross product matrix omega tilde would be omega x minus omega y, omega z. Then you have, sorry, the skew symmetric matrix would be something like this. 0, 0, 0, omega x minus omega y, omega z, minus omega z, omega y, omega x. So instead of a cross product like this, instead of this vector here, you can replace this vector by a matrix like this. And then you can multiply that with this term. Both ways are symmetric. Both ways are fine. And the cross product vector of omega or any vector, if you want to take a cross product, that matrix is always going to be skew symmetric, right? This matrix is actually a skew symmetric matrix, right? And the proof of how to derive this matrix was discussed in the lecture. If you have any doubts, you can always go back and visit to that lecture, or if you want me to discuss it right now, that is also fine, no problem. Right? Yeah, so either ways, if you would like to discuss that, I can discuss that, or we can continue. Okay, so if I'm writing this expression like this, the derivative of this rotation matrix as a cross product of the omega and the rotation metric itself, then this term, you will get the final velocity equation like this, right? The velocity of the position vector q with respect to A is the velocity of position vector B with respect to A plus the the velocity of point P with respect to B, this vector. This is a relative velocity of q with respect to B, that is this term, and this final term, omega cross the rotation matrix multiplied by this position. Yeah. And we would use this principle to propagate the linear velocities and angular velocities, right? Like, for example, if you have a robot manipulator like this, so you can consider all the joints to be vertical. So this is a joint. The joint axis is like this, going up. And this is successively connected to another link with another joint like this. You have another joint like this. And there is also, you can consider a third link like this with a joint like this, whose axis is like this. So I label this as link I. I label this as link I minus 1. And I label this link as link I plus 1. And the joint corresponding to link I is this joint, right? Because, as per the DH convention, if this side is going towards the base, and if this side is going towards the end effector, right? So as per the DH convention, the frame attached to a link is always going to be at the proximal end of that link, right? For example, if you have a link, the end that is closer to the base is called the proximal end, and the end that is closer to the end effector is called the distal end. And we attach the frame of reference for the ith link at the proximal end. So this would be frame I, and this would be frame I plus 1, and this would be the frame I minus 1. So if you want to write the velocity of frame I plus 1, so if this is frame, if omega I is the angular velocity of the ith link, and omega I plus 1 is the angular velocity of the I plus 1 link. And if you are giving inputs to the I plus 1th joint as theta I plus 1 dot, right? Because each joint has a revolute joints or prismatic joints. And for each joint, if you are giving some angular velocity, so how can you relate omega I to omega I plus 1? So you can write it vectorially like this. Omega I plus 1, right? Angular velocity of the next joint is angular velocity of the previous joint, omega I, plus the contribution due to this input, rotational input, theta I plus 1 dot, right? And the way that we would write is we have to represent everything with respect to one frame of reference. So omega I would, if you represent omega I with respect to the ith frame and theta I also with respect to ith frame, omega I will also be with respect to ith frame. But for the sake of propagation, we want this right-hand side to be represented with respect to its own frame of reference, right? So that it can be easily propagated from the 0th link all the way to the I plus 1th link. So if I wanted to convert this left-hand side to with respect to I plus 1th frame, you need to multiply that with this rotation matrix of I plus 1 with respect to I. So if I multiply this equation throughout with this rotation matrix, what will you get? You will get I plus 1 Ri multiplied by I omega I plus 1. This will be I plus 1 Ri I omega I plus I plus 1 Ri I theta I plus 1 dot. So you can write this as, if you multiply this thing out, you will get I plus 1 omega I plus 1. This would be I plus 1 Ri plus yeah. This thing plus theta I plus 1 dot. This would be your final equation, right? And the reason that theta I plus 1 dot does not have a superscript over here is because theta I plus 1 is always expressed with respect to that I plus 1 frame itself, right? So if you have this link I plus 1, and if you have a frame Zi plus 1 attached onto the link I plus 1, the rotation of this link I plus 1 with respect to its own axis is always going to be represented with respect to the I plus 1 frame of reference. So this implies that this I plus 1 is represented with respect to the I plus 1 frame itself. It's a no-brainer. There is also an I omega I here, right? So this is how you propagate the angular velocity from base all the way to the end effector. And you always consider the angular velocity of the base as 0, 0, 0 because base is always fixed. And what would be the angular velocity of the first link? 1 omega 1 would be, as per this equation, it will be, if I is 1, that will be, yeah, that'll be 1 R0. Second. That'll be, I think something happens. Please excuse me for this. So I think my the stylus is not working. So yeah, I hope we can still continue this session. Yeah, so that's it actually. The propagation, I may, yeah, the propagation would be, yeah, 1 omega 1 would be, as per this equation, it will be 1 R0, 0 omega 0 plus theta 1 dot, right? And similarly, you can propagate this all the way to, you can use this to find 2 omega 2, 3 omega 3, so on and so forth, right? That is how you would use that propagation loss. And yeah, that is for this revolute joints. And what would be the case of this prismatic joints? So in case of prismatic joint, you don't have this joint variable, theta I plus 1 dot, right? Because prismatic joint does not have a rotation. It has a sliding input. So the velocity of the prismatic joint is, angular velocity of the prismatic joint is angular velocity of the previous joint itself. There is no new component of theta I plus 1 dot. So this term will vanish for a prismatic joint, and the remainder would be this term only. This will only be a remainder because this thing does not exist for a prismatic joint. So I hope that is clear. This is how we propagate velocities for angular velocities for rotary joints and prismatic joints. And another thing is the linear velocity propagation for rotary as well as the prismatic joints. So earlier, if you can recall this previous expression, how we derived how we derived this expression. I'll just take a screenshot so that we can easily correlate this. If I take a screenshot and if I paste this over here, yeah, forget about it. I'll just, it's better if I write it over there actually. So velocity of Q with respect to A is velocity of B with respect to A plus what are the remaining terms? Position vector of velocity of B with respect to Q, and we have to rotate, multiply that with the rotation matrix plus omega cross rotation matrix multiplied by the position vector, right? And our frames of references were this. We have one frame of reference called A, we have another frame of reference called B, and we have a point, a distinct point, we call this as Q, right? And if I label these vectors, this entire vector from P to Q is position vector of Q with respect to B. And this vector would be position vector of B with respect to A. And the final vector would be position vector of Q with respect to B. And this is the velocity propagation equation. So how do we map this to a case when we have joints like this? So similar to the earlier case. So this is link I. We have link I minus 1 and link I plus 1. And we have a frame of reference attached to link I as Zi, and another frame of reference attached to I plus 1 as Zi plus 1. I hope that is clear. Or if we can use a different ink. This is Zi and this is Zi plus 1. So how would you do this? If you want to find out the velocity of point Zi plus 1 with respect to Zi, using this equation, how would you do that? So you can always consider, instead of this frame P, you can consider this frame B and frame A to be coincident in this case. And you need to find the velocity of this point. The only term that remains would be this term. So this distance corresponds to this distance between Zi and Zi plus 1. And you can consider B and A to be coincident. So instead of this equation, instead of this coefficient A, you can replace this coefficient A and coefficient B by I itself. And for coefficient of Q, you can replace it with I plus 1. So if you do that, it's not straightforward, but that is how that mapping basically comes. Because you are interested to find out the distance between Zi and Zi plus 1, you can consider this to be this distance. And you have to bring this frame B to frame A. So if you do that, if you replace coefficient of A and B as I, and the coefficient of Q as I plus 1, how will you get? So the velocity of Q, that is I plus 1, with respect to I, this will be, since we are considering A and B to be coincident, this velocity would be 0. And this rotation matrix would be identity matrix, because B and A, we consider it to be the same, index. And the term that would remain is this term, that is velocity of, velocity of I with respect to, how would we write that? Velocity of I with respect to I plus, then we would have this term, the angular velocity, omega I with respect to I, because A and B, we consider it to be I, and we take the cross product. And this is an identity matrix because A and B are a unity. And this would now become, Q would be I plus 1, and B and A are same, that is I. And notice that on the right-hand side, if you want to make this as a propagative model, the coefficient of I plus 1 should be written in terms of I plus 1. So you have to multiply this entire expression throughout with the rotation matrix Ri plus 1 with respect to I. So once you do that, you will get the final expression to be like this. Velocity of I plus 1 with respect to I plus 1. That will be I plus 1 Ri. If I pre-multiply this vector with respect to the right-hand side, you will get IVI. Then what else do we have? Plus I omega I cross IP I minus I plus 1. So this is what we get, right? And that is what we have highlighted over here by this equation. And this is the term when the I plus 1th joint is a revolute joint, right? So if you know the linear velocity of ith joint, right? You know the linear velocity of ith joint. You also know the angular velocity of vector of ith joint. Then how do you find out the linear velocity of I plus 1th joint, which is I plus 1. So you do this by this propagation equation, right? Yeah, and this case is when we have a rotary joint, and when we have a prismatic joint, we'll have one more term, that is this equation, 0, 0, d I plus 1. Because if Zi plus 1 joint is a prismatic joint, it will translate along Zi plus 1, so that the translational component will also add up. That is what this term is. But this term does not exist for a revolute joint, right? And for the purposes of this course, you don't have to know how to derive these expressions. You only need to know how to. The only thing that matters is to remember these propagation equations. For the linear velocity propagation for rotary joints and linear velocity propagation for the prismatic joints. And same in the case for angular velocities. And later, when we cover the dynamics, we will further have to extend this to accelerations. Because in dynamics, we'll have to cover the inertial effects. So we all know that this inertial effects are proportional to the acceleration. So that is about it for the time being. We'll stop with the propagation of linear and angular velocities, and that too for revolute and prismatic joints. And yeah, a few more topics actually. So similarly, how we did this propagation of velocities from base to the base to end effector, we will also have to do the propagation of forces, right? So that the mechanism will be in static equilibrium. And but if you take a look at here, the propagation is actually in the backward direction. So earlier it was from base. Velocity propagation was from base to end effector. The propagation of forces or torques will be from end effector to base, right? And this expression is nothing but the propagation of forces, and this expression is nothing but the propagation of moments. And the force propagation basically means, like in case of a robotic manipulator, again, we are considering the case of a 2R robot. So if the robot is subjected to a force or a torque at the end effector, for example, if the robot is supposed to be, bearing a load, which has components Fx and Fy, how much torque should be exerted at each of these joints, tau 1 and tau 2, right? For example, if you are keeping a payload on the end effector, which has components fx and fy, how much torque should you maintain at the joints tau 1 and tau 2, so that the manipulator will be in static equilibrium. So that is the problem that is addressed by robot statics, right? And to solve this force equilibrium condition, you only need to take the free body diagram of each of these links. For example, if I take the free body diagram of this link, the final end effector link. So at the end, you will have the forces Fi plus 1, and here it is nothing but Fi. If I label the forces at the proximal end as Fi and the distal end as Fi plus 1, so for the static equilibrium of this link, the forces at both of these ends should be balanced, right? So this force and this force should be balanced. And if you bring everything to the ith frame of reference, this is how you have to write. Everything should be in terms of ith frame of reference, because you are coming from, it is a backward propagation from I plus 1 frame to ith frame. And similarly, if you are doing the moment equilibrium equation, you have to take the moment with respect to this point. So the moment with respect to that point would be like if there is an ni plus 1 moment exerted by the payload, and at this end it will be ni. So if you take the moment equilibrium of about this point, so the net moment at this point would be the moment at the distal end plus the moment contributed by this force. That is this force multiplied by this moment arm. So if I write this moment arm by p I plus 1 with respect to I, so that moment arm would be this force, this distance cross producted with this force, right? Because this, this moment as R cross F. And similarly to how we did what we did by changing all the frame of references to the ith frame earlier, you can also do this similarly. Everything will have to be expressed with respect to the ith frame using the appropriate rotation matrices, right? So just like the velocity propagation, you will also have this force propagation models, right? Yeah, and that is about it. And the final thing that we would like to cover, final few things that we would like to cover is to map the wrenches between task space and joint space, right? Because we have already done that with respect to velocities, because mu dot is j of q times q dot. This is velocity mapping. And this is task space vector velocities. And over here we have the joint space. And similarly, how do you do this similar transformation in terms of forces and wrenches? So like, for example, if I label the forces in task space, forces and torques in task space as F task space, and tau as the variables in joint space, right? How would you map between the forces in task space and the forces and torques in joint space? So to derive that, you only need to do the principle of conservation of power, because the power consumed in task space and the power consumed in joint space should be equal, because the power is conserved. And power is nothing but the dot product of force and velocities. So in task space, sorry, this is in joint space. So this is power in joint space. And here, this is power in task space. Right? The dot product, tau dot q dot, you can also write this dot product expression as one vector transposed the other vector, because it's still the same operation. So tau dot q dot, you can write this as tau transpose q dot. And f dot mu dot, you can write this as f transpose mu dot. And instead of this mu dot, I'm replacing mu dot with respect to this equation using this Jacobian mapping, right? So I'll get this equation. And if I cancel the q dot expressions here, you can actually find out this the equation for tau dot, right? Tau dot, or tau would be J transpose F, or F would be J inverse transpose. So using this, you can actually find out the forward. You can call this the forward mapping, and you can call this as the inverse mapping. Again, using the Jacobian matrix alone. Right. So that is one thing that we have covered for this lectures, because this is also very important, right? Because as I've said, if the load that a robot manipulator has to carry, if we know that, then what should be the forces that we need to exert on the joints? To calculate that, we can use this mapping, right? And the final topic that we have covered is something called singularities. So the basic definition is, in singular configurations, the number of degrees of freedom of the end effector is inferior to the dimension in which it generally operates, right? Like, for example, I'll demonstrate a singular configuration of a robotic manipulator, or in case of a 2R robot. So if a 2R robot is fully extended like this, right? These are collinear. So both of these links are collinear, link 1 and link 2. What is the peculiarity of this configuration? Right? Because a 2R manipulator should be able to achieve velocities in X and Y components. Right? If I label this direction as X, and if I label this as Y, right? A 2R manipulator, since we are giving two inputs, it should be having velocities in two directions, two independent directions. But when an arm is fully stretched like this, it cannot have a velocity along this direction, right? Because you can see it for yourself. Like, if you fully extend your arm, is it possible to exert a force that is parallel to your arm? That is not possible, right? And what it does is, in this case, when the robot is fully extended, it'll lose a degree of freedom parallel to this axis. It'll only have it'll only have one motion that is perpendicular, right? It can only move like this in a direction perpendicular to this arm, and this component is actually lost. So from all the other configurations, like when it had two independent velocities, at singular configurations, it degenerated, and now it will only have a single velocity, single component of velocity, right? And so that is what a singular configuration is. And typically, this will happen. So singular configurations typically happen when two axes of the prismatic joints becomes parallel, or two axes of revolute joints become identical, right? For example, if you have a robotic manipulator like this, this is one link. It can move up and down like this. And there is also one more prismatic joint like this. So this particular robot will have 2 degrees of freedom. One is up and down like this, vertical up and down, and the other would be side to side like this. Right? So we are giving 2 inputs, we are getting 2 outputs. So if I label the axes like this, if I label this as y and if I label this as x, we'll get 2 velocities along y and along x. Right? But what will happen if both of these axes are parallel? So if both of these axes are made parallel, for 2 inputs, you will only get 1 velocity, right? For example, if both of these joints are made vertical, for 2 of these inputs, you will only get velocity along y-axis. Or if both of these joints are made horizontal, you will only get velocities along x component. Yeah, and similar in the case of a revolute joint. So if 2 revolute joints align like this, if this is one revolute joint, right? And if this is another revolute joint, so if both of these revolute joints align, and if this is a link, so if both of the revolute joint coincide with each other instead of this small distance, so what happens if you rotate this revolute joint and if you don't rotate this? This arm will rotate about this axis, right? So it'll rotate about a larger circle. And if you rotate this arm with respect to this axis, it will rotate about this center. But what happens if these 2 axes coincide? If this distance is 0 and if both of these axes coincide, so no matter if you rotate this joint, the first joint or the second joint, you will get the same rotation, right? Instead of a different rotation about this axis and this axis, if both of these joints coincide, you will get the same rotation, right? So that is also singular configuration. So effectively, it will lose 1 degree of freedom. And this can happen when 2 prismatic joints become parallel and 2 revolute joints become identical. And this is a problem if when you have more number of joints, maybe more than 5 or 6 joints, because in case of a 5 degrees of freedom robot, when it reaches a specific configuration, the revolute joints can become collinear at the specific configuration, or prismatic joints can become parallel. So instead of a 6 degrees of freedom motion, at that specific instant, it can only achieve 5 degree or 4 degree, depending on how many joints are going into singularity. So this is a problem when the robot has more degrees of freedom, right? As compared to 2-hour robots or something like that. In 2-hour robots or robots with very few number of joints, this singularity will only happen at the extremes of the workspace, like when the arm is fully stretched or when the arm is fully folded. But in case of robots that have more number of joints, singularities can happen within the workspace. When either of these 2 conditions are satisfied, right? And at singular configuration, the end effector loses 1 or more degrees of freedom as kinematic equations become linearly dependent. And singular configurations must be avoided as the velocities required to move the end effector becomes theoretically infinite, right? So like, for example, if this is a singular configuration, and if you want to move the robot along this axis, along x-axis, you will need infinite amount of velocity to move it or infinite amount of force to move in this direction, right? Because if you can see it for yourself, if you stretch your arm, if you fully stretch your arm, if you want to move your arm parallel to the axis of the arm, you would need a huge amount of force. So that is also similar in this case, and typically those configurations are to be avoided. So that is how you use this analysis on singularities. And covering onto this type of singularities, there are two types of singularities called workspace boundary singularities and workspace interior singularities. And just like what we have said, this boundary singularities happen when at the end of the workspace, and this interior singularities happen when you have these two conditions, right? When two axes of prismatic joints become parallel or two axes of revolute joints become identical. Yeah, so we will give more examples of singularities as we solve some problems. So we'll solve some few sample problems with respect to the topics that we have covered so far. So yeah, so the first question is, forward differential kinematic model is dash the manipulator in velocity level. It is basically asking the definition of forward differential kinematic model. So which is the correct answer? Is it simulating, or is it controlling, designing, synthesizing, merging, or integrating? So if the participants are still there, you can respond. Otherwise, I shall give the answers myself. So you know the velocity mapping as mu dot as j of q times q dot. And in case of a forward kinematic mapping, you would give the inputs to the joint space, and you would observe what happens at the task space, right? So giving input to the robot's motor and observing what happens at the end effector, it's more or less similar to simulating the robot, right? You'll give some random inputs, observe what that effector does. It's more or less like a virtual simulation. So in this case, the correct answer is it's simulating or analyzing the manipulator in velocity level, right? And that is indeed the answer. And moving on to question 2, for a non-square symmetric square matrix with linearly independent rows, the Moore-Penrose can be written as. So we have seen that in case of this Moore-Penrose is nothing but there are two inverses that we have seen earlier in the lectures. That is Moore-Penrose left inverse and the Moore-Penrose right inverse. So the question specifically asks for the case when the rows are linearly independent. So if that is the case, if the rows are linearly independent, there would be more number of columns. Number of rows will be less than number of columns. So the matrix would be something like a white matrix, less than. For example, it will be like J11, J12, J13, J21, J22, J23. So this is the Jacobian matrix. Mu dot would be J of Q times Q dot. And in case of a linearly independent rows, there will be more number of unknowns than there is equations. So what can you infer from this? So linearly independent rows would basically means that the system is, or it has more unknowns than equations. So that makes this underspecified system. And it can have, for underspecified system, we can have multiple solutions. And we use the solution with minimal norm. Right? That is what we would typically use. And at the beginning of the lecture, we have seen in case of an underspecified system, we would use the right inverse, right? That is Q dot would be J transpose, J transpose the whole inverse, mu dot. And this is what we call the Moore-Penrose, right? Pseudo inverse. Right? And how we got this expression we have discussed in the beginning of the lecture. You can always revisit this the derivation once it has been uploaded in YouTube, or you can also go back and revisit the NPTEL lectures. So that makes, I believe, equation A as the correct answer. Yes, equation A is the correct answer. Moving on to question 3, for a non-square matrix J with linearly independent rows, so it's the similar problem. The following condition is true where J plus is the matrix pseudo-inverse. So carrying over from the previous question, the pseudo-inverse was the right pseudo-inverse, which was J transpose, J transpose, the whole inverse. And it actually says the conditions regarding the matrix, the Jacobian, and the pseudo-inverse itself. So in the case of a right pseudo-inverse, so like in case of when the Jacobian matrix is square, you know that J inverse or J inverse J is identity matrix, right? When J is square. So when the J matrix is not square and we have to use the pseudo inverse, whether the left or whether we have to, if we have to use the left or if we have to use the right pseudo inverse, this may not be true, you know. And the correct answer in this case would be if we are using for right inverse, for right pseudo inverse, J pseudo inverse, only this would be I. And for left pseudo inverse, correct condition would be J pseudo inverse J. This will be identity matrix. Right? So in that case, our correct answer would be J pseudo inverse. This will be identity matrix. And our correct option would be option B. Right? I hope that is clear enough. Yes, solution is indeed option B. And moving on to question 4. For an RR manipulator, the singularity is independent of the first joint theta 1. So is it true or false? So the first thing, you can do this in two ways, intuitively, or you can actually derive the conditions for singularity. That is the second way. So intuitively speaking, if you have an RR manipulator like this, yeah, if you have an RR manipulator like this, so I'll call the first join variable as theta1 and the second join variable as theta2. So when can singularities happen in case of an RR joint? So in case of an RR joint, the singularities happen when these two links align with each other, or when it is fully stretched like this, right? So one configuration would be when it is fully stretched like this. So in this case, theta2 would be 0. Theta2 is nothing but the relative orientation between link 2 and link 1. So this is one fully stretched orientation. And it can realize this kind of configuration in many number of ways. Maybe if theta1 is something like this, theta2 would be 0 like this. It can be like this. So all these are singular configurations. These are all singular configurations, right? When both of these links are aligned, right? So what does that mean? Singular configuration is independent of the first join variable. Can it be true or false? It's true, right? Because it does not matter if what angle the theta1 is. So as long as theta2 is what the singularity is mostly contributed by the second link, because whatever angle theta1 selects, if theta2 aligns with theta1, then that configuration becomes singularity. So that is the intuitive way of analyzing this, or you can also do the conditions for singularity. So the condition for singularity would be is when the determinant of the Jacobian matrix becomes 0. So if you solve for this expression, you will get the conditions for singularity. And if just for the sake of demonstration, I can actually show that. So the forward model of, if I consider this to be the x-axis, and if I consider this to be the y-axis, so the forward kinematic model would be like this for RR joint, would be something like this. X would be L1 cos theta 1 plus, if I call this as L1 and if I call this link length as L2, L2 cos theta 1 plus theta 2, Y would be L1 sin theta 1 plus L2 sin theta 1 plus theta 2. And the Jacobian matrix would be dou x by dou theta 1, dou x by dou theta 2, dou y by dou theta 1, dou y by dou theta 2. Right? And if you do this, the Jacobian matrix would be like this. If you partially differentiate x with respect to theta 1, you will get minus L1 sine theta 1 minus L2 sine theta 1 plus theta 2. And the second column would be minus L2 sine theta 1 plus theta 2. Now the second row would be L1 cos theta 1 plus L2 cos theta 1 plus theta 2. And the final element would be L2 cos theta 1 plus theta 2. And if you take the determinant of this, what will you get? If you cross multiply these two elements, you will get L1 sorry, you will get L1, L2 sine theta 1 cos theta 1 plus theta 2. There is a minus over here. Minus L2 square cos theta 1 plus theta 2 sine theta 1 plus theta 2. Then these two terms minus these two terms, but we already have a minus over here. So that makes it plus L1, L2 cos theta 1 sine theta 1 plus theta 2. I'll just move this over here. Yeah. Then we have one more term plus L2 square cos theta 1 plus theta 2 sine theta 1 plus theta 2. So these two terms get cancelled, right? So I'll just eliminate that off. Now we only have these two terms. So I'll take the common terms out. So that makes it L1, L2 sine theta 1 plus theta 2 cos theta 1 minus cos theta 1 plus theta 2 sine theta 1. Right? So within the bracket, it's like sine A cos B minus cos A sine B. And you can consider this to be A and theta 1 plus theta 2 to be A and theta 1 as B. So the final expression would turn out to be L1, L2 sine theta 2. Right? So this is the condition of singularity. And as you can see, this term is independent of theta 1. So the statement itself is actually correct. For the RR manipulator, the singularity is independent of the first joint variable theta. So the answer is indeed true. Okay, moving on to question 5. It says the workspace interior singularities in a serial robot occur when two axes of the prismatic joints become parallel and two axes of the revolute joints become collinear. So we have actually seen that is indeed the definitions of workspace in interior singularities. So both statements A and B are true. So that makes option C as the correct answer. A and B are true. Because when these two things happen, either of A and B happens, if you are giving two inputs, they are controlling the same output. Right? For example, if you have two revolute joints aligned like this, so I'll call this as Z1, and I'll call this as Z2. And this, if you consider this point to be the output, right? So if you actuate this, or if you actuate this, you are going to get the same output over here. It does not matter, right? Rotate theta 2 by 40, Z2 by 45 degrees, rotate Z1 by 45 degrees. Either ways, you will get the same rotation of this final output point. Or in the case when you have two collinear prismatic joints, so this is one prismatic joint, and this is another prismatic joint. And if you consider this to be your output, and both of these prismatic joints move in the vertical direction, so no matter if you move this or if you move this, you will get the same output for this output point. Right? It will still move up and down like this. If you move either this or this. So you are giving two inputs, you are only getting one output instead of getting two outputs. So yeah, that is where we have workspace interior singularities. But in case of workspace boundary singularities, just like what we have observed for an RR robot, boundary singularities happens at the extremities of the workspace, at the outer boundary or at the inner boundary. But interior singularities can happen within the workspace when either of these two conditions are happening. So that is indeed the case. Okay, moving on to question 6. Yeah, this is a subset of what we have solved earlier. So for a given RR manipulator, the forward kinematic solution is given as so and so. X is A1 cos theta 1 and A2 cos theta 2. Y is A1 sin theta 1 and A2 sin theta 1 plus theta 2. Find the Jacobian matrix of the end effector with respect to the base frame, considering only X and Y. So we know that the Jacobian matrix can be composed by so the basic theory is that earlier I haven't defined much about why the Jacobian matrix is like that. So we know that the function, some matrix basically map the task space and the joint space variables, right? In this case, it will be X dot and Y dot. We have a Jacobian matrix, and what we are mapping are the input variables, theta 1, sorry, theta 1 dot and theta 2 dot, right? This X dot, Y dot are nothing but the velocities of the derivative of X with respect to time and derivative of Y with respect to time. And you can write this equation as the partial derivative of X with respect to theta 1 plus d theta 1 by dt using the chain rule plus dou X by dou theta 2 multiplied by d theta 2 by dt. This is the first equation, and the second equation you can write it as dou Y by dou theta 1 d theta 1 by dt plus dou Y by dou theta 2 d theta 2 by dt. And if you write this as a matrix and vector form, you will get it as X dot, Y dot. This will be dou X by dou theta 1, dou X by dou theta 2, dou Y by dou theta 1, dou Y by dou theta 2, multiplied by theta 1 dot, theta 2 dot. And this is what we have, or this is what we call as the Jacobian matrix. Right? So you have been given X and Y, and if you take the partial derivative of X with respect to theta 1 and theta 2, you will get the first row. If you take the partial derivatives of Y with respect to theta 1 and theta 2, you will get the second row. Right? And with that, if you do that, I believe the correct answer is, so the first element would be, if you take the partial derivative of X with respect to theta 1, that would be, it'll be sign components. There will be a negative sign component here, and there is also a negative sign component here. This is one answer. I believe the answer should be option C. Yes, should be option C. If you apply the Jacobian matrix, if you do the partial derivatives correctly to this forward kinematic equation, you will get the Jacobian matrix as so. Yeah, so the answer is indeed option C. Question 7, for an underdetermined system of equations, the approximate solution is identified from the least square optimization principles. Is that true or false? Like when the system is underdetermined, what is the fact that we have covered earlier? So In case of an underdetermined system, we can have multiple solutions. And these are all exact solutions. These are not approximate solutions, right? So this itself is actually false. Sorry, it's appropriate. It's not approximate. So for an underdetermined solution, we can have multiple solutions. And out of these multiple solutions, maybe I'll write this as Q dot S1, Q dot S2, Q dot S3. Out of all these multiple solutions, we will select the multiple solution which has the minimal norm. Right? From this, we will go with the minimum norm solution. Minimum norm solution. And it is not the least square solution. Right? We go for the least square solution when the system is overdetermined or when it does not have any solutions. We'll go for an approximate solution, that is the least square solution. But in case of an underdetermined system, we go for the solution that has the minimum norm. So that makes this statement false. I hope that is clear. Yeah, the statement says, for an underdetermined system, the minimum norm solution is often selected. For an overdetermined system of independent equations, the approximate solution is found using the least square optimization. So I hope that is clear. Okay, moving on to question 8. The exact solution of an overdetermined system of equations is analytically obtained by solving the least square problem. Yeah, if you are minimizing this objective function, you will get an exact solution. Is this true or false? So like for an overdetermined solution or for an overdetermined system, if the system has independent equations, it may not even have any solutions at all. Right? Because there are more constraints, but we have only fewer variables. And there is no way that we can, make fewer variables to satisfy, all the constraints. So if that is the case, we can, the only possible workaround is to have an approximate solution. It's not an exact solution, it's an approximate solution using least squares. Right? And the keyword that to look here is we can only have an approximate solution. It's not an exact solution. But the question here says we can actually have an exact solution. So that makes this indeed a false statement because whatever we obtain through minimization of the least squares of these two vectors is only an approximate solution. So that is that. So yeah, going for the second last question, it is actually asking us the linear velocity propagation model of the prismatic joint. So like we actually know that the velocity of the I+1th joint is nothing but velocity of ith joint. Plus we also have this component, the tangential component, omega I+1, sorry. This tangential component we have omega I cross, omega cross r, that is that term. These two terms are always going to be there, then plus one term that accommodates or accounts for the prismatic joint. And this is due to the prismatic joint. And because this is a propagation equation, everything from the previous joint, these are all from the previous joint, it will be represented with respect to the ith frame. And in order for us to express everything with respect to the I+1 frame, we have to re-multiply this right-hand side with the rotation matrix I+1 with respect to I. So this would be our velocity propagation for prismatic joints. And I believe our equation's correct answer is either option A or option B. I think it's option B. That is indeed correct. Moving on to the final question. We have been given a Jacobian matrix 1, 0, 1, 1 minus 1, 0, 0, 0, 1, and also a force vector in the task space F as 2, 0, 1. So what does the question say? For a given manipulator, the Jacobian matrix is given as so and so. If the end effector force vector is so and so, then what will be the joint space input vector? So like using the conservation of power, we have derived the expression or the mapping between the task space force vector and the joint space force vector, which was, I believe that expression was tau is J transpose F, right? So if you apply this, J transpose would be 1, 0, 1, and minus 1, 0, 0, 0, 1. And F is given in the question as 2, 0, 1. If you multiply this out, you will get this as 2, 0, 2, 0, and 2, I guess. But we don't have that equation. Did I get this correct? So J transpose would be 1, 0, 1, 1 minus 1, 0. This will be let me check this. Yeah, this is 0, 1, 0. So transpose would be 1, 0, 1, minus 1, 0, 0, 1, 0. So if you multiply this out, you will get your final answer as 2, 1, 2, I believe. So your answer is option B. Yeah, the answer is indeed option B. Yeah, so we have reached the end of our session. And we have also covered all the topics regarding the forward velocity propagation, the forward differential kinematics, inverse differential kinematics. We have also seen how to deal with systems that are non-square when there are more equations than unknowns or more unknowns than equations. How do we derive the pseudo inverses for different scenarios? We have also discussed the mapping or the transformation between the forces in the joint space and the forces in the task space using the principle of conservation of power. We have also derived the forward propagation of velocities and backward propagation of forces. And finally, we have also covered the basics of workspace boundary and workspace interior singularities. And we concluded the remainder of the sessions by solving some sample problems. And now that we have reached the end of this session, we shall wrap the session up and hopefully meet for the next week. So thank you, and we'll see you next week.